Hello, I am Ian Skop.
And I'm Joshua Hoffman.
Today, we're going to talk about MOSFET transistor modeling. Here are the results of the gate sweep for the INFET. The drain terminal was held at a constant 1.5 volts, while the gate voltage was swept from 0 to 1.5 volts. For the INFET, the body was tied to ground. Raw data is displayed in light blue. EKV simulation data is plotted as dashed pink. The threshold voltage is easily identified as 0.4 volts with a threshold current of 1.786 microamps. In the sub-VT region, a linear fit was used to obtain kappa, as the slope of this line is equal to kappa over the thermal voltage UT. UT was readily calculated at 300 Kelvin to be 25.86 millivolts. This value was then multiplied by the slope of the linear fit line to find kappa as 0.67. An exponential fit was used in the above threshold region.
The square root of the source current was plotted versus gate voltage to determine the value of K for the NFET. Such a plot could also be used to find the threshold voltage at the x-intercept of the linear fit line. And the slope of this linear fit line was equal to the square root of K times kappa over 2. This was calculated using kappa from the NFET gate sweep.
Here we see the INFET gate sweep acquired using cadence. Our cadence models were incorrect because the parameter values could not be changed for the simulation, meaning we needed to use the default values provided by cadence. This gave results that were orders of magnitude off.
Here are the results of the source sweep for the NFET. To take the measurements, the drain and gate of the device were held at a constant 1.5 volts, while the source was swept from 0 to 1.5 volts.
Here's the INFET source sweep captured with cadence. We notice the curve is inverted with purely negative source current. We also notice the source current drops off to 0 amps at around 0.7 volts on the source. These errors are likely a result of faulty parameter values used for the cadence simulations.
The NFET drain sweep was performed by holding the gate at a constant 1.5 volts and sweeping the drain voltage from 0 to 1.5 volts. A linear fit was used to model the ohmic and saturation regions of MOSFET operation. The linear or ohmic region of the transistor looks like the IV curve of a resistor, whose slope of its best fit line is equal to 1 over R. The linear fit line in the saturation region can be used to find the early voltage. For our purposes, the early voltage was used to compute sigma. The early voltage is found by extending the best fit lines of the drain sweep measurements to the negative x-axis. Because we only had one drain sweep measurement to work with, the early voltage was found by finding the x-intersect of the best fit line in the saturation region. An example of this is visually depicted by the plot in the top right. The early voltage was found to be 25.421 volts. This value was then used to compute sigma. Sigma is equal to UT over the early voltage. Therefore, sigma is equal to 0.001.
Here is the INFET drain sweep. We notice the magnitude of the source current increases with greater drain voltage, as expected for a drain sweep of the INFET device. The linear or ohmic region can be seen in the subthreshold region, and the saturated region can be seen in the above threshold, where the current starts to level off around 26 microamps. Again, the difference in values between our EKV model and the cadence simulations can be attributed to faulty values used for the parameters.
Here we see a summary of the calculated results.
Here's the gate sweep for the PFET device. For PFET measurements, the body was tied to VDD, or 1.5 volts for the remainder of these experiments. Here the source was tied to VDD, and the gate voltage was swept from 0 to 1.5 volts. The resulting raw data is displayed in blue circles. The threshold voltage was found by inspection to be 0.4 volts, with a resulting threshold current of 34.49 microamps. Kappa was found from the slope of the linear fit line in the subthreshold region. Kappa was determined to be 0.712.
The square root of the source current was plotted versus gate voltage to determine the value of K for the PFET. The gate voltage was swept to determine the linear fit line. The slope was used with the previously determined value of kappa to determine K. The intersect of this line with the x-axis will indicate the threshold voltage of the PFET device. Towards the left end of the plot, we notice the raw data gradually starts to fall off from the linear fit line. This is due to the reduction in carrier mobility with increased gate bias. As the gate bias is increased, the carriers experience more collisions with the surface of the device. This causes a reduction in kinetic energy of the carriers. The resulting drop-off on the plot can be explained mathematically. K prime is equal to the carrier mobility times the oxide capacitance. As the carrier mobility decreased, K prime decreases. K prime is directly related to K, so reduced mobility will cause a reduced slope at significant gate biases.
Here's the cadence simulation for the gate sweep of the PFET. Like the source sweep for the InFET, the curve is inverted about the voltage axis. These errors are likely a result of faulty parameter values used for the cadence simulations.
Here are the results of the source sweep for the PFET. To take the measurements, the drain and gate of the device were held at ground, while the source was swept from 0 to 1.5 volts.
Here is the PFET source sweep simulated using cadence. We notice the characteristic curve of the PFET source sweep with the linear region and the sub-threshold region.
The PFET drain sweep was performed by holding the gate at a constant 1.5 volts and sweeping the drain voltage from 0 to 1.5 volts. The early voltage was found to be 11.498 volts.
Here's the PFET drain sweep. We notice the magnitude of the source current decreases with greater drain voltage, as expected for the drain sweep of a PFET device.
Lastly, here's a summary of PFET parameters.